Hi, this is Mr. Mack. We're back. Now, what I wanted to do at this particular point was to talk about this standardizing uh, equation. So, first of all, let's say that the Wechsler test of mathematical appreciation has a mean score of 82, and it has a standard deviation of 12. And let's say Joanna scores a 118 on the test. Now, if the Wechsler test of mathematical appreciation is normally distributed, the curve looks like a bell curve, but it isn't the standard normal curve, because instead of 0 for the vertical axis, we have 82 here, and then one standard deviation above that would be 82 plus 12, or 94. One standard deviation below would be 82 minus 12, or 70, and so on like that. Now, we call the x any particular score on some data set that's normally distributed a raw score. In other words, it hasn't been standardized. Now, the z-score would be the standard score for the raw score of x. So we can convert these raw scores to standard scores if the data is normally distributed. We can convert them so that they fit the standard normal curve with this equation. Now, the equation would end up being the z-score, or the standard score for 118, would be x, which is 118, minus mu, which is 82, divided by sigma. Now, let's start by considering, I want you to understand what this equation is doing. So let's start by considering this subtraction problem right here, 118 minus 82. Now, first of all, I'm going to ask you this question, and I'm going to pause for a moment, and I want you to think about the question I'm asking. Okay, now, first of all, realize the 118 is x, or the raw score. It's the score that Joanna got on the test. 82 is the mean, and we're subtracting we're subtracting the mean, the average score, from Joanna's score. Now, what is the significance of the number that we get? Here we're pausing. Now, if you need more time to think about this, you can press the pause button on the video, but I'm now going to tell you this is the difference, or how far away from the mean Joanna's score is. We call this the deviation from the mean. You'll notice these words kind of keep popping up. So this is the deviation from the mean. Now, I'm going to point out, if Joanna did better than the average, her deviation is going to be positive. If she did worse than the mean, her deviation is going to be negative. So you have a deviation score, and it is actually a signed, S-I-G-N-E-D, a signed value, where positive means she did better than average, negative means she did worse than average. Okay? Please, don't be like the Florida legislature, which has tried to pass a law saying all scores must be above average. That's really kind of a joke. If you think about it, it is a little silly. Anyway, now, we take the deviation and we divide that deviation by 12. Now, remember, 12 is the standard deviation. So we've got the deviations divided by the standard deviation, and what is the significance of that? Again, let's pause for a moment. If you need more time, you can press pause on the video. Okay, and we're back, I think, I hope. Division tells you how many of the bottom number there are in the top number. So what we're doing is we're taking the deviation of Joanna's score from the mean, and we're dividing by the standard deviation. So the number we get is how many standard deviations Joanna's score is from the mean. And again, if the number is positive, these are standard deviations above the mean, and if it's negative, these are standard deviations below the mean. And this is also a z-score, because z, remember, the units were standard deviations, and so we call the z-score its standard score. Now, if you look at this, 118 minus 82 is 36, and 36 divided by 12 is 3. So Joanna's score of 118 was 3 standard deviations above the mean, or her standard score was a score of 3. Now, we could ask ourselves the question, what is the percent of students who scored less than Joanna on this test? Now, let's just take a look quickly at a standard normal curve here. And 1, 2, 3. Here is where Joanna's score was, and so now the question is, what is the percentage of scores that fell below Joanna's score? Now, you probably know this already, but let's just go through this. If we use the empirical rule, we could say that there are 99.7% of the scores between +3 and -3. Notice also that there's 0.3% to be split up between this region over here and this region over there. So if we divide that by 2, there's 0.15% in this particular region there, and there's 0.15% in that particular region there. So Joanna is above the left 1.15%, but it's not above the right 0.15%. So Joanna is actually 99.85%, or actually Joanna is above 99.85% of the test scores on the Wechsler test of mathematical appreciation. And that's kind of the way we would use that that empirical rule. Now, it is not often, however, that the data falls right on a standard deviation. A lot of times it falls somewhere between one of the standard deviations. And so what we're going to take a look at next is this table. Okay, so in fact, let's go back and let's just set ourselves up a little thing here. Let's use high school male height. Now, let's say the average high school male height is 5'10". And let's say the standard deviation for high school male height is 3 inches. And so we need a male now. How about Arthur? I don't think I have any Arthurs. as students. So we'll have Arthur is 5'4". Okay. So the question is, oh no, 5'4" won't work. Sorry about that, because that's going to be a standard deviation. So let's say he's 5'3" tall. And the question is, what percent of students, of high school male students, are shorter than Arthur? Okay, so first of all, we could look at that. Oh, by the way, you should be told in the problem that the data is normally distributed if it is. And so we're kind of assuming here that the heights of high school males are normally distributed around the mean and the standard deviation. So we're thinking here that 5'10" is the mean, and the standard deviation is 3. So 5'10" minus 3 would be 5'7", and 5'7" minus 3 would be 5'4". And so Arthur's height would be somewhere over here at 5'3". And what we want really is the area under the curve to the left of Arthur, because that will be the percentage of, since the area under the entire curve is 1, that's a decimal that when changed to a percent gives you the percentage of male students that are less tall than Arthur. I hope that makes sense to everybody. People in class, would you nod your heads yes if you're getting this? Okay, I'm seeing some nodding and I'm seeing some jazz hands here. So let's continue on and hopefully it'll make sense. I'm suspecting that those of you that are watching the video are feeling kind of the same way. But now here's the thing. If we standardize this score, in other words, the z-score for 5'3" is going to be 5'3" minus 5'10" over 3 inches, because that's the standard deviation. In other words, x minus mu over sigma. Now 5'3" minus 5'10" is negative 7 inches over 3 inches, gives us negative 7/3, which is negative 2.333, with the 3's repeating. And there is a question. Hang on just a second here. And we're back. Now, see, what we're going to look at is we're going to look at this z-score, and what we want is the area under the curve to the left of that z-score. Now, look with me at the table. I've split this into two so that we can read it on the screen. But notice here we've got a normal curve, and the z-score is right here, and what it gives us is the area to the left of that particular z. And we're back. Now, again, z is the standard score, and this table gives us the area under the curve to the left of that value. Now, what we're looking for is we have a z of negative 2.3333. Now, this table will only let you use a z to the nearest tenth. So we're going to use negative 2.3 as our z-score. That's the best we can do here. Now, what we do, I'm sorry, 2.33. We can use 2 decimal places, okay? So what we do is we look along the side for negative 2.3, and then we go across on this top one till we get to 0.03. Now, if you added 0.03, negative 0.03 to negative 2.3, you would get negative 2.33, and that gives us this value right here. So we would say that the proportion of students that did less well than Arthur. Let's go back to where was Arthur? Was Arthur here? No. There it is. There's Arthur. So we get a z-score of 0.0099. Was it 0.00 or just 0.099? It was 0.0099. So we would say that 0.99% of the students did less well than Arthur on the test of mathematical appreciation. So it's possible, and we're back, it's possible to use the table of areas to the left of a particular z-value to find the percentage of students, or the percentage of something that is less than that. Now, if we wanted the percentage of students that scored greater on the test of mathematical appreciation, we would we would have 100% minus 0.99%, which would be 99.1% scored higher than Arthur did on the test of mathematical appreciation. Now, I'm going to pause this video. I'm going to split this video up, so I'm going to make another rendering here, and we'll come back for a third one.